Here we go. We are starting a new section. This is section 2.5, implicit differentiation. So what we're going to be dealing with, and the reason I've been emphasizing all the different notations like dy over dx and all that kind of stuff, is because we're really going to be working a lot today with dy over dx, okay? Implicit differentiation sounds really fancy, but it's just a fancy way for saying, hey, if a problem isn't solved for y, how do I take the derivative? Okay, so I'm going to show you how to do that today. So let's fill in the blanks. Let me refresh your mind on a little bit of algebra stuff, calc and algebra stuff. First, if I say, we know that derivatives are rates of change, right? We know that, of a moment in time, okay? And then if we are taking the derivative, we are taking it, listen to this phrase, with respect to whatever is there, right? So this is the derivative with respect to y. So we call it dy over dx, right? It means that we're measuring the rate of change with respect to x. So for example, you'll see something like y equals 3x to the fifth, okay? What about this? Do you look at this? D over d theta, right? That's the derivative of y with respect to theta, right? So did I say with respect to y? I meant with respect to x. I'm sorry. I think I said, anyway, I'm sorry. Let me go back to this one. Derivative with respect to x of y. This is the derivative with respect to theta of y. And so we have finally the derivative of s with respect to t, okay? So you would see something like s of t, like our position formula, right? And this would be y equals sine theta. So let's fill in these blanks. Which one, I'm going to have you guys fill in the blanks with independent or dependent, okay? So looking at, and this is the algebra part, okay? Looking at y equals 3x to the fifth, which one is our independent versus dependent variable? So y is the blank variable and x is the blank. What do you guys think? Y is independent? Is that what you think?
No, y is dependent.
Y is dependent? Change is depending on x. Yeah. So y is the dependent variable and x is the independent. Because right, couldn't I plug in anything for x, right? And get it pops out a function for y or an answer for y. So in this dy over d theta, y equals sine theta, is y still dependent on theta, right? Yeah. So y is still dependent. It depends on what you put in for theta here, right? And x is the independent. Okay, you can abbreviate DEP and IND if you want. ds over dt. So changing with respect to t, it's whatever is on this bottom here, dt or dx or d theta. So I guess it's taking a while to pop up. So s is the dependent. Does that make sense? It depends on t. Whatever you plug in for t, it pops out something for s, or s of t represents s. So, and I'm sorry, that should say t. Oh, I didn't change those. This should be theta. Sorry. Theta right here, and this should be t. Okay. T is the independent. Okay. So basically, our dependent variable is what you solve for. All right, y equals. Okay. So if we have up until this point, we've been doing explicit differentiation. When I say differentiation, what do I mean? Take the derivative, right? That's why I kept throwing out those terms. So explicit means it's complete, it's clear. Explicit means clear. So it's completely solved for y. So that's all that means. Solve for y, that's your blank. I got a lot of setup here before we do an example, so. And then so like all the problems that we differentiated with respect to x have been solved for y or for f of x or g of x. So these show that the variable y is written explicitly as a function of x. So for example, here, I'm going to show you what we've been doing and what I haven't written because it wasn't necessary, okay? And this will show you how we deal with implicit differentiation. So what we were doing, and you can write this with me for example 1, is when we were taking the derivative, we would take the derivative with respect to x of both sides of this equation, right? So we would really take, we could write this as like d over dx of this side and d over dx of this side, right? The derivative with respect to x. So then if I were to, every time you take, so listen to this, every time I would take the derivative of something, if I take it with respect to y, it's dy over dx, right? If I take the derivative with respect to x, it would be dx over dx. So here's what it would look like. I would write, what's the derivative of y? It's just 1 times dy over dx, right? Equals, what's the derivative of 5x squared? 10x dx over dx, right? Plus 9, derivative of 9x is 9, dx over dx, right? Why would I not write dx over dx? What does that equal? 1. So we would go straight to this step. We would say, hey, y, I can write y as dy over dx, right? Because that means the derivative. And this is just 10x plus 9. So I never wrote any of this junk here because it was silly to, right? We didn't have to. But now there's going to be a need to write it, right? So this is taking the derivative of x with respect to x. It cancels to 1, okay? This is taking the derivative y with respect to x. So that's one way we can do it, okay? Example 2 is going to show you implicit. Are we good to move on? Okay. Okay. If a problem is written implicitly, it is not solved for y. Go ahead and fill in that blank. Okay. So basically, if I can easily solve it for y, I might want to, right? But if there's a lot of problems out there that it's really not easy to solve for y, it's a nightmare. And you can, so it's just like, hey, I'm just going to take, it's easier to take the derivative as it is. And so we have a method to do that. Okay. So this right here, do you see that this is written implicitly? It is not solved for y, right? Let me ask you a question. Is this problem pretty easy to solve for y? I would say so. And that's how I would solve it. If I were given this problem to take the derivative of, I would solve it for y and say y is 1 over x, and then I would solve it explicitly, okay? If you can do that, that's usually the easiest way if it doesn't create anything more complex. So I would say, hey, y is x to the negative 1, y dy over dx, I'm going to use dy over dx since that's the theme for today, is negative 1 x to the negative 2, right? You could use quotient rule if you wanted, but, and that would be negative 1 over x squared, right? That's the derivative, okay? Easy peasy, and then you don't have to do the new stuff. However, are you ready for an example where we have to use implicit differentiation? Okay. I know we're still writing. I'll give you a second. So there will be times when it won't be as easy to express y explicitly. And for those times, that means we can't solve for y. We are going to use, here's your fill in the blank, implicit differentiation. Okay, so what I mean by this, if you take the derivative of y, if we derive y, we write dy over dx. Okay, if we derive x, we take dx over dx. If we derive a constant, this is what's weird. We write d constant over dx, that we just kind of write that. Okay. If you derive a cat, you write d cat over dx. Okay, do you get the point? Right? It's d of whatever you're deriving over dx, or whatever your dependent variable is. Later on, it's going to be theta. Okay, I'll show you examples with that. Okay, so let's try this one. Looking at this, is it easy to isolate y? No, it's all gross and mixed up. And so I think I see all independent terms. Is it easy to take the derivative of every part of that? 100%. It's really easy to take the derivative of each term there. There's no product rule or anything, right? It's really easy. So here's what we're doing. We're gonna take the derivative of this whole thing with respect to x. So every time I take the derivative of x, I have 2x dx over dx. Now, do you see my note over here? I'm going to be overkill in this first example, okay? And I'm going to write everything like the dx over dx. You won't have to write dx over dx or d constant over dx. I'm just write it with me just so you can kind of see what happens. And I will show you what you won't have to write. So 2x dx over dx. What's the derivative of negative 2y cubed? Negative 6y squared. And what do I write next to it? dy over dx. And then I'm taking the derivative of y again. So it would be 4 dy over dx. And then equals, what's the derivative of 2? 0. So 0 times d constant, just squeeze it in, d constant over dx. Okay? It's d constant, right? So what I have written in blue, we are normally going to skip this step, okay? Okay, so in black, you could go immediately to this next step. Do you understand dx over dx is just 1? So we would write 2x minus 6y squared. We still have to write the dy over dx's plus 4 dy over dx is equal to, what's 0 times constant, d constant over dx? 0 times anything is 0. Remember, dy over dx or dx, like these derivative notations represent tiny little infinitesimal pieces. They're really small, right? They're changes in something. So it's the rate of change. So it's 0 times the number is 0. Now, so you can go, do you understand? You can go from here to here immediately, from that to this step. Yeah, that's how we're going to write these. You don't have to write dx's over dx's and d constants. Okay, so the goal here, what do you think the goal is to do? Solve for what? dy over dx, doesn't that represent the derivative, right? So what you want to do is group all of your dy over dx terms and then solve. Okay, I have a more explicit way to explain that in the that's coming up, but this is just to show you. So do you understand? I'm going to get this negative, this 2x on the other side. I'm going to subtract it over, right, to group those dy dx's. So I would have negative 6y squared dy over dx is equal to negative 2x. Now, what do you think I could do to solve for dy over dx? Well, we don't want to divide what? Yeah, well, first I'm going to factor it out, right? And then, so you could, yeah, so you already kind of did that in your head, but you factor out a GCF of dy over dx. Typically we factor it out, all right? And we write, well, we have negative 6y squared plus 4, and then we divide, as you guys were saying. So we divide by this negative 6y squared plus 4, whoops. You get your final answer is dy over dx is negative 2x over negative 6. I mean, I don't like negatives hanging out there. I'm just going to switch it up and write it as 4 minus 6y squared. It just looks nicer. We like to do that in math. We like to be fancy. Yes. Since. Okay. So here's another way to write this. You could write this as, if you brought this negative to the denominator, you'd have to distribute it. So I could write this as 2x over 6y squared minus 4, right? So I could do that. I'm glad you brought that up. That's a great question. Okay. I could write that kind of multiple ways. Could you reduce by a factor of 2? Yeah. So you could also write this as, right, negative x over 2 minus 3y squared. or this as x over 3y squared minus 2, okay? So kind of however you want to simplify that is how it goes. All right. So flip to the next page, and I'm going to give you some guidelines for these. I already showed you them. I felt like it was better to show you than to like have you write it. So now I'm going to have you write it. Okay. Also, do you see that I want you to do something important for homework tonight? Do you guys have an extra note card? Okay. So you need to make a note card for implicit differentiation. Okay. I would maybe put any important facts from this chart. Okay. Let's fill it out. So this is basically summarizing what I already like told you. We differentiate both sides with respect to x. Anytime you differentiate it, you follow it with the d term over dx, or whatever your independent variable is, right? Could be theta, could be t, right? So dy over dx, dy over d theta, ds over dt, whatever. Okay. We usually don't write them for constants or your dependent variable. Okay. This is just recapping what I said. Then we solve for dy over dx by getting all terms with dy over dx on one side of the equation. And then everything else goes on the other side. Isolate dy over dx, often done by factoring. Okay. And finally, to solve for dy over dx, you just solve by dividing, like we did. That's typically what you do. There's different techniques, but for different problems. Okay. Do you want to try the next one? Okay. Not really, but we're going to do it anyway. I appreciate the honesty. It's fine. All right. So give this one a shot. And remember, you don't have to write dx over dx or d constant. Okay. Give it a shot. Hit me with your best shot. Anybody have a question? Oh.
If you mean what were we supposed to write? Dy. I was trying to get dy over dy over as soon as you get to
oh yeah.
then it'll be d constant.
There that would help you remember. Right.
Yeah, that's right down that too.
When you would look back, I oh now I
just to like think of it.
And then I would put an example. This is probably how goes it?
It goes.
You guys ready for me to write some steps? All right, we're taking the derivative of this equation with respect to x. So we do 3y squared. Anytime I take the derivative of y, I need to write dy over dx. Okay. Derivative of y with respect to x.
Can you explain what the respect means?
Oh, with respect, oh, because we respect x. No, oh yes, see. So no, it's because, listen up. Is anybody else confused about this with respect to x? Yeah. So with respect to, listen up. With respect to means regarding x. It just means we're talking about x. That's all it means. It's like taking the derivative and x is my independent, or x is my sorry, I said that right the first time. X is my independent variable. So I'm basing everything on x. Yeah? Okay.
Why we have the d over x.
Yeah, so that's why dx over dx cancels out, because everything's based on it. So it gets a free ride, kind of. Yeah.
So it's our important. Thank you.
Yes. It's the bell of the ball. Okay. Derivative of y squared, 2y dy over dx. Derivative of negative 5y minus 5 dy over dx. Derivative of negative 2x. Do I need to write anything? No, not for x. It's fine. And then negative 4 derivative is 0. It's a constant. You don't need to write anything. How'd your first step go? Good? Okay. Now what did you do next? Yep. Subtract, add the other one over. So we're going to add 2x and then group everything else, right? Okay. Tell me if this is too much in one step, let me know. I'm going to add the 2x over. And you understand I have to get all three of these and take out a GCF of dy over dx. Do you guys want to just do that in one step? Right? So if I factor out a dy over dx, I'm left with 3y squared plus 2y minus 5. Understand? Or do you have a question? Okay. Does anybody want me to write the in-between step? I can. Okay. All right. So then you divide by all of this. Boom. And you got your final answer. Dy over dx is 2x over this business. That's it. I'm not going to make these incredibly hard or anything. I don't know what you're going to see in college, but implicit differentiation was kind of like, hey, here's implicit differentiation. Moving on. And it kind of leads into what I'm going to teach next, which is I'm going to be more heavy on for that.
Isn't there like an app or something that you can look at your professors or like a website that like gives you reviews?
RateMyProfessors.com. Yes. Yeah. I use that all the time.
Just the 5 saying,
Ah. Yeah, sorry, I forgot my minus. Thank you. Minus 5. Yeah. Okay. How much do I have time to do example 4? I know Holden has to leave early. Yeah. Let's do it. What?
College, can I just say I don't need to do it?
You show up, you gotta flash your light. Somebody please do that and tell me what they say. That'd be fun. Yeah, you're good to go. I would say watch example 4 because we're gonna get it. All right, let's do example 4 and then we'll finish the other 2 tomorrow. Okay. Or not tomorrow. I mean, do you guys know where you're going tomorrow? You're going to period 2 for attendance. Anyway, okay. We'll finish it on, we don't have school Monday, we'll do it Tuesday. Okay. Example 4. Okay, check this out. Do you guys know what calculus rules we're going to have to use for this one? Product rule. How many times? Twice. Do you see it? We got product rule here and product rule here. First D last plus last D first. So let's do it. Anytime you take the derivative of y, dy over dx. Okay. So first D last, I'm taking the derivative of y, which is 1. Normally I wouldn't write it. I would just write dy over dx. All right. I took the derivative of y, so I got to write dy over dx. Yeah. That's first D last plus last D first. Do I need dy over dx? No, because I derived an x. I wrote a y, but I didn't derive it. You only write dy over dx when you derive. Differentiate it, okay? That's first D last plus last D first for, whoa, sorry. Okay, for this part. That's for the first one. Now we have to do product rule for the second one, okay? Which is going to be plus first D last, which is 1, plus last D first, 2y, need to write dy over dx equals 0. Good. Any questions? So we're reusing all of our rules we learned. Let's clean it up. We have x squared dy over dx plus 2xy plus y squared plus 2xy dy over dx. What do we have to do? Yeah, so the only terms I want on this left side here are these 2, right? So I'm going to subtract everything else over. Okay. I'm going to subtract over my 2xy and my y squared, right? You don't have to write this part in red, but I'm just showing you that's what I'm going to do. Okay. X squared dy over dx plus 2xy dy over dx. If you feel comfy with the algebra, I'm okay. If you automatically just factor out your GCF as well as you're adding things over, subtracting things over, that's fine. Minus 2xy minus y squared. And then I take out my GCF, dy over dx. We factor it out. We write what's left, x squared plus 2xy. And it equals this business. And then last step, divide. Boom. Plus 2xy. Okay. Keep in mind the next section is like word problems and it involves like some of this stuff. So your final answer is that dy over dx equals that. Okay. Hey, for homework, just do that. Make sure you do your note card, please. Okay. That's the only thing you have to do tonight.